So thank you, the OWASP team, and I'm super excited to be a part of the OWASP 20 anniversary. My name is Barak Schoster. I'm working with Palo Alto Networks, and we are going to talk about policies, code, graph theory, and we have some other cool stuff on the agenda. The talk has 5 super easy parts. I know that the graph theory might be a little intimidating, but we will make it really simple for everyone to understand and start using it right after. Um, so we'll start with talking about what is policy as code. We'll introduce graph theory. No panic from combinatorics or mathematics. We'll not dive into that deep. We'll take a step further into an open source tool named Chekhov, and we'll see how we can write graph policies or policy as code using that tool. And from there, we'll talk about how graph theory and threat modeling are a little bit of connected. So let's start. I thought about this talk for a long while, and I thought that to explain what policy as code is, I'll take you through my very biased evolution on a nonlinear timeline, getting exposed to security policies in different organizations. Today, I'm working on making YAML configuration being exciting, like a lot of DevOps engineers. So I thought to give it a shot and try to make this YAML configuration exciting once again. So when policies were introduced to big enterprises, the first phase was really policy as paper. My journey began when I started as a young software engineer in a startup, and I then moved into a big enterprise and had a chance to work on policies a lot of times. And it was, at the beginning at least, very manual. On Kubernetes, for example, there are 263 pages of established best practices written by very smart people, business committees, regulations, that came up with those set of best practices to how to secure your data center or your cloud environment specifically for a Kubernetes infrastructure. After a while, enterprises have started to work with auditors to enable expansion of business and make sure that the right methodology and tools are in place. Other best practices outside of DCAS like ISO, SOC 2, GDPR, PCI, if you work in the financial industry, started to emerge and adapt to cloud architectures. Auditors asked questions like, where do you store your data? Who has access to production environment? What is the process to gain that access? Are you following secure development principles like OWASP Top 10? And it was all good. As security practitioners and engineering teams, we started to have discussion on what should the market look like, what should be the standard. And it was the job of the auditor to guide us through that process. It was the job of the director of engineering, CISO, CTO, CIO, or others to answer all of those different questions on those environments, and are those environments following best practices. We had spreadsheets over spreadsheets and tons of documents. The ment was very good, but the implementation of having policies was really a tedious manual task and really a boring task to have. The good news is that another group of smart people got opinionated and changed the format of policies paper to a collaborative paper. Confluence and Jira came into our policies lifecycle and help us to manage the risk. So we can collaborate on policies as security practitioners and threat models that our application architecture has. And we've created dedicated policies that are best matching to our team. So we don't have a generalized 263 pages. We have dedicated pages on a collaborative portal now, and a set of tasks on a ticketing system that converted policies to tasks that DevOps teams and IT teams should take. But it still was a very manual task, more collaborative, but still manual. Shoving tickets down the backlog of different application tips And it's really hard to keep up as the application kept growing. So another group of smart people came, and they created a set of scripts, Bash, Python scripts, etc., to continuously audit on an hourly or daily basis our VMs, databases, later on serverless functions, Kubernetes pods, and their networking configuration to see if they are compliant with policies and best practices. And if you are extremely using those scripts, you even added a step that automatically create a ticket within your ticketing system like Jira and assign it to the matching owner of cloud resources if there is any drift from best practices. So this helped cloud security engineering team or InfoSec team to scale their efforts auditing those cloud environments on all different servers. But it inflated the SRE's backlog. The SRE teams have lately transitioned to provisioning cloud resources from manually or from scripts to different infrastructure as code frameworks, enabling creating microservices and to deploy them multiple times a day into production. So this solution of monitoring based on hourly basis, on daily basis, really was not talking with those tools and those methodologies of infrastructure as code. Infrastructure as code is a set of ways to provision cloud resources in a collaborative manner instead of a manual task. And creating tickets on top of those really created a lot of friction and frustration with SRE teams. Let's take a look on the SRE's job. Previously, SRE teams have provisioned cloud resources through the different cloud provider consoles. Then they moved into automations, writing some bash scripts, and we can provision a new VM, a new EC2 instance, pretty easily using a set of bash commands. But what about stuff like reliability, debugging, reusability, collaboration, versioning, and security? Where would those be configured? And let's take this example. We have a web server configuration and a security group. The web server have port 22 open to the entire wall, meaning I can do SSH connection to that web server. And the web server is attached to that firewall group, to that security group. So I can configure now a web server in a very descriptive way. And it's just as I did live, I can review as part of a collaborative process together with the security engineer what configuration is good in that specific web server and what configuration should be fixed. The cloud configuration, when you're using infrastructure as code, saves states. So you can automatically deploy, tear down, or see the current structure of your cloud infrastructure, and it's immutable. So now DevOps engineers can make sure that they can collaborate and can debug and configure reliability and backups on resources. And everything is stored in code and version control, and we can roll back to different versions and make it very repeatable and scalable. And for the purpose of this talk, we can make it more secure. With infrastructure provisioning in code, security needs to happen in code as well. But that's easier said than done. Infrastructure as code allows us to manage the sprawl, but introduces also complexity because you can have your configuration scattered around across different repositories, across different teams, and your configuration can be really messed up. And this is where cloud DevSecOps can, powered by automation, can really help us. So now we can see that each commit over the history can be tracked. We can track the owner of it, and we can review as security team what should be fixed on a specific configuration. It's better, but we're still missing the automation of security around it. Before diving into how we'll implement security, let's take a look on what's the situation out there. At Bridgeview, we've scanned thousands of Helm charts and Terraform repositories from the open source GitHub, Artifact Hub, Terraform registry, and various other sources. And we were curious about our hypothesis of how many misconfigured templates there are there in the wild, in the open source. And we've discovered that almost half of the available open source modules of Terraform is misconfigured, and a lot of Helm charts are not compliant as well. And the kind of misconfigurations that we've seen are various, from lack of logging, insecure protocols, unencrypted databases. And together with our research team at Palo Alto Unit 42, we've discovered that 95 of the cloud security issues are actually related to misconfig. Where on the open source repositories that we've scanned, 43% of the cloud database were not encrypted, which was important customer data potentially at risk. And 60% of the cloud storage services did not have logging enabled, which made it really difficult to review an audit trail of events that are security related to incidents. Those different configurations can be risky and can provide remote access to those cloud resources and can be used as an attack vector. In addition, security risks obviously can impact business. Misconfigurations corresponds to compliance benchmarks. And in order to be compliant with a specific framework like SOC 2, HIPAA, PCI, you must follow a set of configuration guidelines. And the DevSecOps aim is not only to find misconfigurations, but to prevent them very early on, democratizing the process to developers, and really catch it before it applies to the cloud configuration. So another problem that we have is the ratio between security teams and development teams. One of our issues there is that the ratio is really one security engineer to 100 different developers, and it's really hard to review those misconfigurations manually over GitHub, over each pull request, over each code change, and we want to scale that process. One insecure infrastructure template can lead to 100 different deployments and thousands of alerts. And we have multiple ways to deploy infrastructure as code. We have hundreds of security configurations for cloud resources, and we have a lot of cloud providers, and it's really getting hard and not really sustainable. It's hard to keep up the pace of new services being created. Some of them are even not real over the different cloud providers. And it's really an endless journey trying to keep up the pace of new services being provisioned, new code being written within our org. And it's hard for us as security practitioners to keep up that pace. And engineering are not happy either, because security is coming after the fact and not part of the development lifecycle. And what we want to change is from moving from a 3-month cycle and long security reviews that does not always make sense into an agile process where we deploy in each end of sprint of 2 weeks or 3 weeks and have a scalable security cadence as part of this sprint process. We want the feedback to be very early on, and we want to solve the root problem of each misconfig. And we can't expect devs to be the security expert, or actually can we? So let's try. Some other smart people have gathered and have created a linter, an ability to inspect the code of those cloud configuration very early on and to write tests on infrastructure that will make it secure and make sure that there is best practices in place, making it developer first and codified, automated, and integrated to the development lifecycle. The dev-centric approach to cloud security put infrastructure as code at its core, enabling teams to develop secure infrastructure at the same pace as they're developing reliability or scale. providing automated feedback very early on. So let's see how tools like Chekhov can help. We have an understanding what a misconfig are and that it's important to address them, but let's try to find and fix a misconfig. So we've written Chekhov. I'm actually one of the maintainers. Chekhov was introduced at the end of 2019 when we struggled to find a tool that will help us to inspect the configuration pre-provisioning. Since then, Chekhov today have more than 3 million downloads, deployed in tens of thousands of CI pipelines, and it has really good community adoption around it. More than 100 different contributors and more than 1,000 policies helping to inspect different frameworks of infrastructure as code, such as CloudFormation, Terraform, Kubernetes, ARM templates, Helm charts, AWS CDK, serverless, Docker files, and the list goes on. You can point Chekhov on a specific directory and let it scan your infrastructure and to inspect it by these thousands of policies. Chekhov can also be deployed on top of CI/CD and can help us to fix the source issue. So if we have an S3 bucket like the following one that does not have versioning enabled, we can actually identify using Chekhov what are the missing lines and fix them for you. So let's start with installing Chekhov. So the thing that I'm going to do is I installed Chekhov and I've executed here the results. Let's do it again. We'll run pip install Chekhov and we'll take a look on our Terraform file. We'll run it on a specific directory with a specific policy ID. And we'll see that we do not have versioning enabled on our S3 bucket. And the policy looks like this. We have a specific attribute that we want to inspect, which is versioning, and we want to make sure that it's enabled, and the resource type is S3 bucket. Pretty simple, 9 lines of code, and you have a policy that is inspecting an attribute. Let's try to make it a little bit more complicated. A real-life scenario would not need only to inspect a specific property, because on a 3 tiers web application, we have a lot of resources that are building our architecture. On the following example, we have a user accessing a website through a DNS record, a CDN, and CDN has a dependency on the files that are being served, that are stored in S3 bucket. The application server has a load balancer that is connected to a set of VMs in EC2s in AWS. Those specific VMs have an SQS that is doing data processing, an auto-scanning group that is attached to a database, and we have also an file storage that is attached as a mount to that set of VMs. And when we try to analyze what is the security posture of such environment to do threat modeling, we really want to inspect attributes and properties, not of a single resource, but on the dependency of them, trying to understand if an actor can actually access the storage through a movement through those dependencies. So we need a strategy to create dependency-aware policies. And we need a way to democratize the process of threat modeling, which is not scalable, to all of our engineers. So let's dive in to graph theory. This is a node. A node represents a code block in our infrastructure as code that might be dependent in other code blocks. Our code block has a set of attributes like versioning for S3 bucket and can be represented in a graph as a specific node. And we have an edge. Edge is the connection that represents the dependencies between two nodes. So for example, if I have a VM, I can see what is the connected volume of storage by traversing this edge. And this is a DAG, a directed acyclic graph. The DAG represents the connections between different resources or the dependency between different code blocks. And the last operation that we will do on this graph is actually a walk. We have Pikachu here. Pikachu can move from one node to another node by traversing the specific edges. While doing that, asking what is configured on each edge and what is the attributes of those edges. So if we have our web application, we can try to ask traversing policies where we can translate this specific architecture to a directed acyclic graph, and we can ask Pikachu to traverse and try to identify if, as a result of dependencies, we have a misconfigured environment. Do we have a threat? So let's create a policy. I created a graph policy in Chekhov. Again, Chekhov is open source, and you can always use it under Apache 2 license that try to understand if my EMR clusters have security groups that are open to the world. Are they public? It's an obvious question, but it's hard to check that, because to check that, I need to inspect all of my EMR clusters, traverse over all of the connected security groups, which is the AWS Cloud Firewall rule equivalent, see that the connection exists. For each security group, I need to check that there is a CIDR block that is not open to 000, which is the public internet. So I need to check that I have a security group that is connected to the EMR cluster, and that it has a variable that represents the CIDR block, and to validate if it's 000. So in Chekhov, we've built this graph that helps us to identify the different connection between code blocks. Here is an actual code block of an EMR cluster of the production engineering team that is connected to a security group that is actually public and bad. And it's bad because of the dependencies. This specific block is not bad as a standalone block, but as a result of the connection, it's exposing the EMR cluster for an attack. So that's how graph theory works with infrastructure as code, and how does it build into Chekhov internals. When Chekhov reads an infrastructure as code like Terraform or CloudFormation, it creates in memory directed acyclic graphs. And it can use two types of policies, either attribute-based policies written in Python, like we've seen on the beginning on S3 bucket versioning, and graph policies that more resembles of a threat modeling process. And it lets those different policies to scan the graph and gives us the results. And it can be implemented across the development lifecycle. We can have Chekhov on the IDE, the pre-commit, the pull request, CI/CD, and runtime phase. The more early that you're running Chekhov, you will democratize the process of validating code and fixing it, but you'll have less context to the production environment. So the more left that you go, you are fixing the problem more early on, but less production context. And as you go forward from fixing in IDE to the pull request phase, you get more context like environment variables that are only accessible in the CI and make impact on your cloud configuration. And on runtime, you have the most context, but the highest complexity to fix, because it's very late on the process. You don't always know who's the engineer that made that change, and you need to triage in order to fix. You can integrate Chekhov as part of GitHub Action and actually fail a build if it has a violation of a specific policy. So taking a step back, what does the graph abstraction enables us? We heavily understanding that it can traverse, and we have a specific example of public EMR clusters that we want to prevent, but what other examples are there out there? Other examples that are available as part of the open source policies is, for example, to ensure that EBS volumes that has a dependency or an attachment to VMs, to EC2s, are encrypted, making sure that all of the data stored on our servers is secure. We have another one, which is making sure that S3 bucket have a dependency in public access block and is made private
RDS have backup plan, and other use cases. And the more extreme use cases would be, let's attach CVEs into that graph, and let's also attach the runtime instance of that resource into that graph. So actually, what Graph gives us within Chekhov is a solid data model that gives us room to evolve from testing to threat modeling very early on, shifting that left or giving it the DevSecOps experience. It also grants you the capability to join the open source community. So Chekhov had hundreds of policies being contributed by open source users in amazing companies. So you're more than welcome to go into our website, to Hacktoberfest blog post, and to understand where to start and contribute policies that will be serving the entire OWASP community or CNCF community, helping to democratize and solve very early on threat modeling issues that you might experience in your infrastructure as code. Thanks a lot.